Welcome again. This is a selection of test questions that I asked in the summer of 2017 over the Kinetics chapter, chapter 14 of the chemistry textbook. Hopefully this will give you a good feel for types of problems. By watching this, hopefully you'll have new insights of how to work through various kinetics problems. Thank you for your patronage.
Problem 1, we discussed the issue of comparing the production of hematite to the consumption of magnetite. Here, we're given the problem that hematite is produced at a rate of change in a rate of 2.5 moles a day. So the rate is 2.5 moles. Doesn't matter the units as long as the units are the same. And we're asking what is the rate for magnetite, Fe3O4. Well, our ratio is really the coefficients. We say that these two are equal by a factor of 1 over 6 to 1 over 4. And it's technically negative because this is being consumed, this is being formed. But so what do we have to do? We take that 2.5, divide it by 6, and in order to get this number, we have to multiply it by 4. Technically negative 4, but we'll live. So we do that math, and we get 1.67 moles a day, or B. Problem 2. We're looking at consumption of nitrogen and ammonia production is a first order process, so that how much of a 3 atmosphere sample of nitrogen is left after 85 minutes. If the half-life is 20 minutes. So we're saying, what is A sub t if A sub 0 is 3 and time is 85 minutes? We need A sub 0, we need K, we need T. But we don't have K. Fortunately, we have the half-life is 20 minutes. ln 2 over 20 will be used to get our K. We do that and we find K is equal to 0.0346 per seconds. Now we're going to plug that into here. So 0.0346, inverse minutes, my bad, times 85 minutes plus natural log of 3. Plug that in, you get 1.84. And so you have ln A sub t equal to 1.84. So to get A sub t, we just have to take the inverse log of both sides. Inverse log cancels out that. Inverse log cancels out that. And you get how much is left? 0.158. And that is the answer. Answer A. Problem number 4. We look at a second order decomposition of HI. Second order equation is 1 over concentration at time t equals K times time plus 1 over the initial concentration. And our half-life is 1 over K over the initial concentration. So they say we want to go from initially 500 grams. Here's where I was tricky this year, to 1 milligram. So 1 milligram is 0.001 gram. And after 50 milliseconds, it takes 50 milliseconds to go from 500 grams to 250, which is defined as the half-life. 0.050 seconds. So, solving for K is what we do first. So we say that K is equal to 1 over a sub 0 t1 half, 1 over 500 times 0.050, and you get K is a really small number. Really small number, 0.04 meters to the inverse 1, seconds to the inverse 1. Now, we're going to plug this back in and solve for t. So we have 1 over 0.001 equals 0.04 times t plus 1 over 500. So 1 over 500 is equal to, well, a really small number. We're going to take this and say subtract 1 over 500 to both sides. And that gives us that 999.898 equals 0.04 t. We're going to then divide both sides by 0.04 to get t by itself. This is going to be also a big number. Get t is equal to 24,999.95 seconds. That doesn't match any of our current answers, but you notice the current answers all have different units. So I'm going to turn seconds into minutes by dividing by 60, and then turn minutes into hours by dividing by 60 again. And you get this is equal to 6.9 hours equals t, or answer D. Problem number 7 is another second order problem. It took 50 minutes for the concentration to decrease from 15 grams to 0.52 grams. And as what is the half-life be for the initial 15 gram decrease? So in this case, I have all I need to find K, and then we're going to need K to find our half-life. So 1 over 0.52 equals K times 50 plus 1 over 15. Once again, we're going to subtract 1 over 15 from both sides. And that's going to give us 1.853 equals 50K. We're going to divide both sides by 50. And that's going to give us our K of 0.0371 inverse meters inverse seconds. What inverse minutes? It's 50 minutes. Finally, for the original 15, plug that number in there. Our t1 half is 1 over 15 times 0.0371. We solve that and we get the answer to be 1.8 minutes, or answer B. Problem number 10 involves a reaction diagram. See here, where we're going from reactants to products through a transition state up here. So, as we work our way through this, I ask what is our activation energy and what is our delta H, our enthalpy. Enthalpy is just the difference in energies between products and reactants. -40 minus a negative 57 gives us positive 17 kilojoules. Those are in units of kilojoules. Now, that's our delta H. Our activation energy is the difference from our starting point and the highest point. How much energy does it take to get up to that peak? So negative 23 minus a negative 57 gives us the activation energy is positive 34 kilojoules. And obviously, the activation energy would be less going the other way. Problem 11 is a rate law problem. We have to find the K of this rate law. In order to find this K, we need to find the order of A and the order of B. So we need to compare two equations where B doesn't change and two equations where A doesn't change. So for B, we're going to look at equation 1 and 2. It's going to have B cancel out, and A cancel out. We want 1 and 3. So we're going to compare the rate of 2, 3.98 10 to the negative 5th, divided by the rate of 1.43 times 10 to the negative 5th, equals K over K. They can be cancel out because they are constants. A to the M over B to the M can be sucked into the same thing of A over A to the M. And same thing with B over B. Only thing is that any number, any time 1 is raised to any exponent, we still have the number 1. Those cancel out. So what we have is, do that up, sum is 2.78 equals 1.66 to the M. Now there is a fancy logarithmic way to determine M, but because I'm giving you this problem, your best bet is the order is a whole number, either 0, 1, or 2. If the order was 0, this would have to be 1. If this is 1, well, those numbers would have to be the same. So let's try 2. If you try 1.66 squared, you should come up with 2.78. So that tells us that M is 2. Well, let's compare 1 and 3 now. 1 and 3, so 1 is 1.43 times 10 to the negative 5th. B is, 3 is 4.78 times 10 to the negative 6 equals K over K cancels out. A over A still cancels out, and we're left with 0.075 or 0.025. Do that math, you get that this is 2.99, and B is essentially 3. And that leaves the only possibility as N being 1. So that, with that in mind, we have our rate law. Now we just need to plug one of these numbers in to get K. The beauty of this is if you set this up correctly, any of these experiments should give you K. I can use experiment 4 if I so choose. Rate of 2.66 times 10 to the negative 6 equals K times A squared times B. Well, since I have to isolate K, we're going to divide these from both sides. And that will give us our K. Our K ends up being 3.4 times 10 to the negative second, or answer C. Problem number 13. We're looking at how much of this radioactive tin would decay in 71 years of human lifetime. We're given that the half-life of this is, with a big number, 230,000 years. We're given that we're starting with 1,000 grams, and we're told how much would remain, how much will have decayed in 71 years. Not how much will remain. Not A sub t, we don't care about that. We want A sub 0 minus A sub t. How much would have been lost? Step 1, we have to find our K constant. So we're going to say ln2 for our half-life, 30,000, gives us our K, which is a really small number because, well, it's radioactive, and that means we're dealing with a really long time. It's a really slow reaction. There's our K. Now we have everything we need to start solving this. So we say, we're solving a negative, really small number, 30136 times 71 plus natural log of A sub 0 equal, which is natural log of 1,000, equals natural log of our product. We solve that, and once we do that, we sum all that up, and we're going to take the inverse log of both sides to find out how much A sub t remains. And we find out, oh, that's almost nothing. We're down literally like 99.8 grams remains. Meaning that if we want to know how much is decayed, it's 1,000 minus 999.8. If we didn't round, the answer would be up to 214. But I did round in those numbers, so we get 0.2. But either way, the same number. Answer A. Well, number 14 is not one of my best problems. It is the only one I have right now of a rate law. And it will clearly show the two most important things in writing a rate law. So we are given the reaction. 2NO3 forms 2NO2 and O2. It's described by a rate for K times NO3 squared times NO2 determines our speed. One of the products is going to help make this reaction faster. And you're asked which of these rate laws is described by these two facts, that reaction and that rate law. What are these two mechanisms? So the two things a mechanism needs to do, it needs to match the overall reaction, and it's going to have a slow step determine our rate law. So first thing we can immediately cross out is if the sum of both of these reactions doesn't add up to the overall reaction. So this guy, the sum, 2 NO2s, crosses out with 4 NO2s. So we have 2 NO2s, 2 NOs, 2 NOs, those cancel out. We have a O2 on here, and we have a 2 NO3s. So the overall equation matches. That one is still valid in the running. NO3, NO3, so 2 NO3s. NO2, 3 NO2s, so still 2 NO2s. There's an O2, there's a NO and NO. Still valid. NO plus NO3, we have 2 NO3s, no NO3s over there. 1 NO, 1 NO, NO2, 3 NO2s, still valid. So 2 NO2s. All these so far are valid. 2 NO3s, no NO3s over there. NO2, 3 NO2s, cross out the NO2s. And NO, cross out, and we have O2. All these are valid. As written, it's a valid mechanism that could happen. Now, whether they will match the rate law is to be determined. Now, there's no equilibrium in here, so we're not throwing out anything too hard. But basically here, the rate determining step, the reactants of the rate determining step, will matter when it comes to when we look at the rate law. So let's look at B first, because that's the only one where the rate determining step is the first step. So the rate law we get from that rate determining step is NO3 to the first times NO2 to the first times K. Because that's a rate determining step, the amount of NO3 and NO do not matter for that case. So, does this match this? No. So, that is not the one. We don't want B. Now, you may be asking as you look at this, well, there's an NO2 on the reactant side and NO2 on the product side. NO2 hasn't changed. Yeah, it's just acting as a reaction body. NO3 is bumping into NO2, and it's dropping an oxygen as it does that. So that NO3 is serving a the NO2 is serving a purpose, even though it's not abundantly obvious. So this guy, the rate would be K times NO squared NO3 squared. Which, no, that doesn't match, but we didn't put NO in there. NO got generated by NO2. So the amount of NO, that NO squared, is approximately proportional to NO2 squared. So it actually becomes K NO2 squared NO3 squared. Once again, does that match all rate law? There's no, A is not. Let's look at C. We have rate is going to be NO3, NO2, and the amount of NO2 is going to be dependent on NO and NO3. So it's actually going to be really complicated, but needless to say that square root of NO2 is equal to essentially 1 square root of NO and NO3. No matter what, even if you're like, what the hell is he doing with square root? The idea is that NO would be present in the rate determinant in the rate law. We do not see an NO in this rate law, so it is clearly not C. While that leaves only D as the option, let's check and make sure. So the rate law will be K equals NO and NO3. Once again, NO, we did not put the NO there. NO is going to come from step 1. So it means that's going to be equal to NO3, NO2. Plug those in, we get K equals NO3 squared NO2. The first, oh, hey, that matches our rate law, and they add up to be the right reaction. That is a valid mechanism. That is what we're looking at. Valid mechanism. The products and reactants have to add up to get the overall reaction, and the rate determining step has to match our rate law. Problem 15. Problem 15 immediately follows this one, saying, and looking at the mechanisms here, and which mechanism is NO a catalyst? So NO is neither a reactant or a product, but it either is formed in the middle or formed at the beginning. So we're looking at where is NO a catalyst. So we can break down reactions into 3 parts: reactants, products, catalysts, and intermediates. Reactants and catalysts can be the same. Reactants and intermediates can be the same. But a reactant is something that we form in the beginning and is usually gone by the end. Product is something we didn't start with, but we form at the end. Now, catalysts and intermediates are the hard ones. Catalyst is something that is consumed initially, but reformed by the end. And intermediate is something that is formed in the middle, but doesn't hang around very long. So in that case, we're looking for which one is NO in the first equation as a reactant, and the second equation as a product. There's NO in the middle, the end in the beginning. There's NO at the end and at the beginning, at the end, then the beginning. Only in equation C is NO a catalyst, where it's at the beginning and the end. So mechanism C is NO catalyst. Problem number 16 is the dreaded Arrhenius equation. Now, this is the hardest one, but if you break it down, it is not nearly as bad as you would think. So the reaction has a rate constant, or K1, of 2.04 times 10 to the negative fifth at 0 degrees Celsius, which is our 273 Kelvin. The rate constant is 5.39 times 10 to the negative third when the temperature has been raised to 80 degrees, which is 353 Kelvin. And I ask you, what is the activation energy? What is our E sub A? The only thing we need right there is R, which is 8.314 joules per mole Kelvin. That in mind, we can simply plug in our numbers and evaluate and isolate our R. So, we have natural log of 5.39 times 10 to the negative third divided by 2.04 times 10 to the negative fifth equals negative EA 8.314 1 over 353 minus 1 over 273. So I'm going to evaluate what I know. So I know I can figure out the L and K, 5.58. And if I do this math, so equals negative EA over 8.314. I do this math, that is negative 0.00083. Now, I I multiply both sides by R, by negative R, and I divide both sides by 0.00083, and we get EA by itself. We get EA as 55894, and you got to remember, oftentimes EA is given in kilojoules. So we divide that number by 1,000, we get 55.8.9, or answer B. That concludes the kinetics review.